Okay, so we're on to line 18A, 3S2. No-hair theorem, black hole, 4-dimension event, horizon, redshift, Wow Seti, part 123. Again, Wow Seti signal comes to that number. Here's all the tags that we're going to talk about. And we'll go back up here. So the no-hair theorem postulates that all black hole solutions of the Einstein-Maxwell equations of gravitation and electromagnetism in general relativity can be completely characterized by only three externally observable classical parameters: mass, electric charge, and angular momentum. All other information for which hair is a metaphor about the matter which formed a black hole or is falling into it disappears behind the black hole event horizon and is therefore permanently inaccessible to external observers. It is considered a theorem by physics. So again, we've got another theory here. There is still no rigorous mathematical proof of the no-hair theorem, and mathematics refer to it as the no-hair conjecture. So I'm assuming, if it comes up in the Wow Seti signal, then maybe it is true and it does exist. And maybe we'll find out how or why. So, four-dimensional space-time. The no-hair theorem was originally formulated for black holes with the context of a four-dimensional space-time, obeying the Einstein field equation of general relativity with zero cosmological constant. In the presence of electromagnetic fields or optionally other fields such as scalar fields and massive vector fields, Proca fields, spinor fields, etc. Proca comes up quite a bit. Extensions. It has since been extended to include the case where the cosmological constant is positive, which recent observations are tending to support. Magnetic charge, if detected as predicted by some theories, would form the fourth parameter possessed by a classical black hole. This is an event horizon. It says inside the event horizon, space is being pulled faster than the speed of light. And it seems to go this way, and the singularities down there, light is pulled in, light escapes, light is stationary. So this is event horizon. In general relativity, of course I had to look it up, right? Because I don't know what it means. In general relativity, an event horizon is a boundary in space-time beyond which effects cannot affect an outside observer. In layman's terms, it is defined as the point of no return. So basically, once you're in there, they think you're fried. The point at which the gravitational pull becomes so great as to make escape impossible. It kind of reminds me of those Star Trek movies, right? Where they got stuck in something and then they blew up and they couldn't go. There was always a sister ship or something that it happened to. The most common case of an event horizon is that surrounding a black hole. Light emitted from beyond the horizon can never reach the observer. Likewise, any object approaching the horizon from the observer's side appears to slow down and never quite pass through the horizon, with its image becoming more and more redshifted as time elapses. The traveling object, however, experiences no strange effects and does in fact pass through the horizon in a finite amount of proper time. More specific types of horizon include the related but distinct absolute and apparent horizons found around a black hole. Still other distinct notions include the Conchi and Killing horizon, the photon spheres and ergospheres of the Kerr solution, particle and cosmological horizons relevant to cosmology, and isolated and dynamical horizons important in current black hole research. I looked up four-dimension space. I wanted to see if I found a graph, and this is what we came up with. Future, elsewhere, past. World lines of light. Okay. So that's supposed to be 4 dimensions. I don't know if that's correct or not, but these are called absorption lines from spectrum. In the optical spectrum of a supercluster of distant galaxies right, as compared to the absorption lines in the optical spectrum on the sun left. So there's difference in the lines. Arrows indicate redshift. Wavelength increases up towards the red and beyond. I don't know what that means. But anyways, check this guy out. He's floating midair. Looks like he's having fun. He looks a little scared though, there, right? So he's one of the greatest minds in the science and space world. So in 1981, Stephen Hawking, I believe this is Stephen Hawking right here, floating in midair, and James Hartle came up with an imaginative proposal. So here we got another imagination in the works here, and it's quite cool, which promised to avoid the singularity at the origin of the universe, and also gave an answer to the question of why there was no time before the Big Bang. But before we can consider the theory, we need to introduce a couple of concepts. Again, that's their faculty.umb.edu. So in 1983, I found this picture here. I thought it was cool. So Hawking has spent much of his time trying to develop a quantum theory of gravity. So again, we need his theory of gravity to see what we can do with it. He started out applying his idea of Euclidean quantum gravity to black holes, but in 1983 he teamed up with Jim Hartle at my camera's flashing. It's out of battery power. So there's expanding universe, and I don't think we're going to get through all this. We're getting a lot of data about black holes, speed, velocity, and measurements of the universe showing up in the data. I don't quite understand any of it at this point. I hope as we go along. Keywords that show up a lot in the last 3 sections of data is Minkowski spacetime. And then there's this black hole here. And then this one here is high energy physics theory, entanglement interpretations of black hole entropy and string theory from Brustein, Mark B. Einhorn, and Amos Yarom. You want to take a look at their papers. They talk about black holes, entanglement. They use the integral method to define the Hartle-Hawking